Okay, so on Monday, we had previously done resistance and current. No, that's not right. We previously done voltage and current. And then we talked about how voltage and current are related to each other. Remember, we talked about the word proportional, and that brought us on to resistance. Okay, so in order for current and voltage to be proportional to each other, resistance must not change. Remember, we said that? And then I told you about Ohm's law, which is the relationship between voltage, current, and resistance. And I gave you these 3 questions to do. Okay, so we'll do these. So your formula is V equals IR. Now let's see what we have. Calculate the voltage across a resistor of resistance 5 ohms. So 5 ohms is a resistance. If the current flowing through it is 3 amps, that's a current. Okay, so let's put them in. So V we don't have, so leave it as V. I is 3, so I'm going to put it in as 3, and R is 5. Remember that between I and R there's a multiply sign, so we are multiplying 3 by 5, which is 15, and the unit for voltage is volts. That's the first one. Second one, I'm going to start with my formula again. Calculate the current flowing through a resistor of, so 30 ohms is a resistance, when the voltage across it is 12 volts is a voltage. Okay, so again, fill in what you know. So V is 12. I we don't have, so leave it as I. No, just that's an I, not a 1. And then R is 30. Okay, so a little bit of algebra required here. We want to isolate the I, which means we need to get rid of the 30. At the moment, the I is being multiplied by the 30, so we need to do the opposite of that, which is to divide by 30, and that will take it out. But if you divide by 30 on the right, you're going to have to divide by 30 over here on the left. You must have balance. Okay, so on the right now, all I have is I. And on the left, I have 12 divided by 30. Oh, sorry. 12 divided by 30, which is 0.4. And current is measured in amps. All right, and the last one. So formula again. I'm just going to change colour because it's a bit close. Calculate the resistance of a resistor when a voltage of 6 volts, so that's a voltage, causes a current of 2 amps, so that's current to flow. Same again, fill in what you know. So V is 6, I is 2, and R we don't know. We're trying to isolate the R, and at the moment it is being multiplied by 2. So we need to do the opposite of multiply by 2, which is divide by 2. That will eliminate the 2. But if you divide by 2 on the right, you have to balance and divide by 2 on the left. So now I'm out of room, but on the right hand side we just have or, and on the left hand side we have 6 divided by 2, which is 3, and resistance is ohms. Okay, so the first answer should be 15 volts. The second answer, 0.4 amps. And the third answer, 3 ohms. So obviously make sure that you have the number correct, but you also have to have the units, okay? It's very important in physics that you include units, so make sure your units are right. Okay, so hopefully that went okay. I will be back on Monday. So what my plan on Monday is for that class to do like a recap of, what the hell was the chapter before this one? Oh yeah, okay, no. So do a recap of this chapter, and then this day week we'll start into our acids and bases experiments. I just want to make sure that you're okay with electricity, so we'll do a couple of exam paper questions and kind of open up for questions, anything you're unsure of, given you were taught this online. And then next Friday we'll do, I have my experiment list, don't I? Here. Yeah, so next Friday we should get number 1 and 2 done, and then we'll get 3 done the Monday we come back. Okay? Or even if electricity is okay, we might do 1 and 2 on Monday and 3 on Friday. So we'll figure something out, okay? But we'll get through it all as quickly as possible. But I just want to give you an opportunity to ask a few questions on electricity because we haven't done a lot of physics, just to make sure it's okay. Anyway, the very last thing in this chapter is connecting bulbs in series and in parallel, okay? So this is in a circuit. When you connect bulbs up, there are different ways to connect them. You can either connect them in series or you can connect them in parallel. When I was younger, like when I was taught science and specifically physics in school, it would have been quite normal to have, the Christmas lights you put up on your tree. They would have been connected years ago in series. Okay, so you'd have like 100 lights all connected. In series means like this, so you'd have a bulb, a wire, a bulb, a wire, a bulb, a wire. So they're literally like that in series with each other, which was grand and all. But what happened was, if one broke, there was a fault in one, every single one of them broke. Okay, so when this was taught to me, as soon as that was said, everybody remembered the horror of trying to do this on Christmas morning. Whereas obviously now you probably won't have experience with that because most lights are now not in series anymore. But yeah, you need to know the difference between bulbs wired in series and bulbs wired in parallel, although most bulbs for practical purposes are wired in parallel now. Let me show you. Now, where did I put it? Okay. All right. So here's one I made earlier and all that because they take a while to put together and I didn't want to be boring you with it. Okay, but what we have here, up here is our battery. I put a switch in. It's always a good idea to put in a switch for safety. And then down here, you can see I have a wire which goes into a bulb, a wire into a bulb, a wire into a bulb. Okay, so these are connected in series. Okay, I can't write on this, but actually, you know what? Hang on. So bulbs in series. Okay, so I want you to make sure that goes into your copy, what it looks like to have bulbs in series, okay? And this is in series, okay? In series means when they are in the same or on the same path. Okay, when they're on the same path, that's what it means to be in series. Okay, now I just want to briefly show you something, okay? So I think there's a way to switch it, is there? Oh yeah, see here, right? At the moment, obviously they're using like little pictures, like that's a picture of a battery and little picture of a bulb or an animation or whatever. Most of the time when we draw circuits, we draw it using the component diagrams, okay? So I just want to switch it. Okay, so this is a component diagram. So, oh no, go back here. Right. So let me show you what a component diagram would look like. Okay, so what we would have is for a battery, this is the component diagram. Okay, it's a long line and a short line representing the positive terminal and the negative terminal. Okay, wires are just straight lines. Okay, as straight as can be. This here is an ammeter. It measures current. So that is shown with an A in a circle. And then if we go down here, so a switch actually looks a bit like what it looks like there. Okay, that's what a switch looks like. And then your batteries they look like little ohms like this. Sorry, your bulbs. I said batteries today. I meant bulbs. Okay. So this over here in red is the component diagram. Okay, if you were to draw your diagram the way it's drawn over here, you would have to label it. You would have to write battery, bulbs, wire, switch, and ammeter. Okay, but if you draw it the way it is over here as components, these are universally accepted symbols for the different parts of the battery. So you draw it this way and you don't have to label it at all. Okay, and now all the symbols are actually in the formula and tables book. I can't remember where it is in the contents, but if you have a look at the contents, you'll see components, something to do with component parts or circuit components or something like that. And they're actually all there, so you don't even need to remember them. Okay, so in your notes, I want you to take down both versions of this. Well, actually, do you know what? I definitely want you to take down this one. Okay, if you feel like you also need to draw the one on the left, that's fine. Okay, but this NB, not bene, that's the important one. Okay, now, right, so I was saying these bulbs are connected in series. Okay, so I'm going to close the switch, and there you have it. They're moving, and each of the three bulbs, you can see the electrons passing through the bulb, and as a result, the bulbs are lighting, and you can see the light around them. Okay, but look what happens when I break a bulb. Okay, so I'm going to break the middle one. They all stop. And it doesn't matter which one you break. Here, I'll break this one. They all stop. Break the other one. They all stop, okay? Because they're in series, when you break a bulb, you are breaking the path. And as a result, nothing flows. Okay, so in series, if one breaks, they all go out. Okay, now let's look at the parallel one. Okay, so here we have the one, sorry, I'll just break this for a sec. So there it is, stopped. Here's the parallel. So here I have my battery and I have an ammeter in again. I have a switch over here for safety. But now look what I have, okay? Can you see where the word parallel comes from? So these are on parallel paths. Oh, don't break it. These are on, the bulbs are now on parallel paths. So as opposed to being the same path, they're on different paths, parallel to each other. Okay, and if I close it, you'll see they all come on. Okay, so again, I'm going to just snip this one out. Okay, so bulbs in parallel, just make that a bit bigger. All right, so there you go. And again, if I was drawing it, there's my battery, wire, ammeter, go down. It's drawn slightly differently. Okay, so here's my first path and my bulb, second path, bulb, sorry, I'm going to do them backwards here, third path, bulb, okay, and then those paths recombine and they go up here. Oh, try that again. Go here, I have a switch, and there you go. Okay, and I'll just put my, okay, so again, okay, that's after sticking, so I won't move it. Anyway, the one in black here on the right is the component version of the one on the left. Again, if you were to put the one on the left onto an exam paper, you'd have to label everything. Okay, so watch what happens now when I break one. Okay, so I broke the first one, but there's still a path. See the way the electrons in this path here have stopped? But it doesn't affect this path and it doesn't affect this path. Even if I break another one, that middle one will keep going. So because they're on separate paths, if you break one, it doesn't mean they're all broken. And this is the way the bulbs in your house are wired. So that if the bulb in the living room goes, you don't lose all the power to every bulb in the house, because that would be crazy. You know, if somebody disconnected the bulb downstairs by accident and you lost every single bulb in your whole house, it just doesn't make sense. So they're wired like this. They're wired in parallel, so that if you were to take one bulb out somewhere in the house, all the other bulbs would keep working because they have their own path. Okay, so I'll try and write this, but I don't think I can. Right. So, oh, it worked. So when bulbs are wired in parallel, if one breaks, the others continue to work. Okay, massive benefit of wiring bulbs in parallel over series, and now pretty much everything is wired in parallel for that reason, just for convenience. Okay, so I have two questions up here. Where are they here? They're from your book. So you want to draw a diagram to show three bulbs connected in parallel to a battery. Now add a switch in the diagram so that all three bulbs may be turned off at the same time. Okay, so I don't want you to draw it, I want you to make it. Okay, just in case anybody's having problems getting to this, if you go PHET, like obviously it's saved because I use it a lot, but if you just Google PHET, you'll find it. Okay, and now down here on the left we go physics. I'm going to turn off chemistry and actually I just want electricity. Sorry. Okay, so if you just take electricity and you scroll down, and here you have Circuit Construction Kit DC. If you go into that and hit play, that brings you into a blank version of these. Okay, so what I want you to do is I want you to go into them and I want you to draw a circuit to show three bulbs connected in parallel to a battery. Now add a switch to a diagram so that all three bulbs are turned off at the same time. And then I want you to do the same thing, three bulbs connected in parallel to a battery. And now I want you to add three switches so that you can turn off each bulb independently. So I did it there by just hitting the disconnect button, but I want you to make it using a switch. And it would be great, I mean, if you have to just build it and take a screenshot of it and that'll be your homework, it'd be great if you could make a little video, a little iMovie or something, explaining the difference between the two circuits that you're going to build. So the first one where you have one single switch that will turn them all off, and the second one where you have three switches where you can turn off one and leave the other two going. Okay, so I'd like you to build those circuits. At the very least, I'd like a picture, but ideally a video would be great so that I can actually see the animations working and you can show me turning off the switches and turning them back on. Okay, so that is due for Monday, so I'll actually be in to receive that homework, which is amazing. So please make sure it's done. You can upload it to Schoology if you want. But yeah, I'll be coming around to check it in class on Monday. Alright, so have a great weekend and I will see you Monday.